Our little redox interlude continues with this mini lecture on oxidation of alcohols and aldehydes. Now that we know oxidation states, we can see that alcohols are more highly reduced than those CO double bond functional groups. So, just to, kind of continue on keeping us straight on where we are skipping most of Chapter 19 at this point. We have covered the catalytic reductions, and now we're going to look at kind of the opposite end of the spectrum. We are now going to turn to oxidations. So oxidation-wise, the main things that we want to oxidize are alcohols. That's the good news. The bad news is, the main stalwart oxidizing agents that we use are just gruesome. Chromium is the main culprit, as we shall see, but I'm going to try and emphasize some new reagents on the scene that fit in nicely into the green chemistry realm. Alright, so let's review by what we know about reagents for reduction and oxidation. Reducing agents, of course, add hydrogens. So we haven't exactly learned this one. That we will save for a little bit later in the course, but clearly we learned that if I add hydrogen in the presence of a catalyst, I'm going to get down to the alkane or the alkene. So reducing agents add hydrogen. Oxidizing agents, therefore, must do the opposite. They remove hydrogen. And the whole chemical background of this is that if they're removing hydrogens, there's got to be a driving force, and the driving force is that these oxidizing agents are in a very high oxidation state, and they want to be reduced. So I already mentioned chromium. Chromium 6 is a great oxidizing agent because it really wants to get reduced down to chromium plus 3. Manganese plus 7 would really like to be reduced down to manganese plus 4, and so on and so forth. We will, believe it or not, we'll see halogens like our zero-valent halogens being reduced down to halides. Halogens are actually great oxidizing agents. So, in all of these cases, what is happening is your alcohol's hydrogen, a hydrogen on the same carbon as the hydroxyl group, is kind of miraculously being removed, thereby oxidizing that carbon, as you can see. If this is a 0 plus 1 minus 1, then we've got an oxidation state of 0 over here, but now we've gone up to an oxidation state of plus 2. Alright, how does this work? Well, there's one mechanistic step that you need to focus on. You take your alcohol and somehow or other you do something to it. You add something to it that's in this box that is ready to leave with a pair of electrons. So you're reacting your alcohol with a reagent that puts this thing on there, this thing that's in a high oxidation state and really wants to accept electrons. And if there's a hydrogen, as we suggested in the previous slide, if there's a hydrogen on that same carbon that bears the hydroxyl group, then exactly what needs to happen is this. A base will remove that hydrogen just exactly like an elimination reaction. Kick that pair of electrons up into the carbon-oxygen bond and give those electrons to the thing in the box. So it really is a lot like an E2. So now leaving is, now let's get real. What is that thing in the box? And as I've already said, chromium is one of the most effective oxidizing agents there is. It's still very widely used, but it's just it's a bad actor in terms of toxicity, environmental harm, and all of the above. So what are our chromium reagents that we rely upon? Chromium trioxide is a nice inorganic solid that is, as you can see, highly polar, dissolves very well in water to give you chromic acid. And if you just do a quick scan here, you can see that they're both in the +6 oxidation state. 2 + 2 + 2 + 6 + 6. So they're ready to be reduced. Furthermore, with all of those dang oxygens on there, you know they're pulling electron density away from chromium and making those chromium atoms really, really electrophilic and susceptible to attack by a nucleophilic oxygen. So, piece of cake, without going through the whole mechanism on this slide, you're adding your alcohol to the chromium, is making an intermediate that allows that key step to take place, and you've gone from an alcohol to a ketone. Here is an important thing to recognize in all of this chemistry. I have essentially done the deed of removing that hydrogen, making the ketone, and now there is no more hydrogen on the carbon bearing the oxygen. Without that hydrogen, no more oxidation can take place. The reaction is over. It doesn't matter if I have tons and tons of chromic acid in there, no further oxidation can take place. Alright, and the byproduct here is the reduced chromium, which we will see as we look at the mechanism in a little bit more detail. So chromic acid is really acidic, and my nucleophile is going to attack my electrophilic chromium to give me, and now I'm just going to go like so to keep it simple. Here's my hydrogen, this is my ethyl group, and I have Cr, OH, OH, double bond O, OH. Okay, so I've gotten to that intermediate, a base, probably water. In fact, let's be real, let's use water because this is in aqueous conditions. Can deprotonate that. H. Ketone this. Alright, so chromium works great. But here's the thing. If I use a primary alcohol, if I want to oxidize a primary alcohol, as you can see, I have 2 hydrogens on the carbon bearing the hydroxyl group. So I get that key intermediate. That intermediate then is the one that's going to give me, oops, get that off of there. It's too small for me to write here, so that goes right there. And then the chromium gets reduced. In any case, you end up with the aldehyde. Great. There's many times I want to oxidize an alcohol to an aldehyde. This is great, right? But the problem here is, when I do this, what you can see is the aldehyde still has a hydrogen attached. So, aldehydes, being carbonyls, they're good electrophiles too. And even though I've undergone an oxidation, I can go further. More oxidation can take place. Because since aldehydes are good electrophiles, and I've got a good nucleophile present, especially since I'm under acidic conditions, this happens in a heartbeat. This is called hydrate. And as you can see, once the hydrate is formed, what do I have? I have the key requirements for further oxidation to take place, because that can react with the chromic acid that's still present to make that darn intermediate again. And that darn intermediate can, of course, undergo the key oxidation step to give me an even more highly oxidized species. So I've gone all the way from -1 primary alcohol up to +1 in the aldehyde state. But, and here's the key, because I have water present, I can make the hydrate, With the hydrate, I can make the chromate ester. With the chromate ester, oxidation takes place again. And if I wanted to stop at the aldehyde, I didn't. And that makes me mad, because I wanted to. Maybe. Sometimes. So, selectivity is an issue. Just like we looked at selectivity in the reduction of alkynes to alkenes to alkanes, we have the same problem when doing oxidations. How do we stop when we want it to stop at the aldehyde? Well, there's the answer right there. If there's no water present in this reaction mixture, then I don't get the hydrate. If I don't get the hydrate, I don't get the chromate ester. If I don't get the chromate ester, I don't get the acid. So, guess what? This takes us all the way back to chapter 1 because it's all physical properties. Here's the thing. We use water because that's what chromic acid is soluble in. We use water because that's what chromium trioxide is soluble in. Can we come up with a good oxidizing agent that's not that polar and doesn't require a polar solvent like water to dissolve? And the answer is yeah. We can definitely make something more nonpolar because we just figure out a way to put a whole bunch of carbons and hydrogens in it. It's got carbons and hydrogens in it, then it's nonpolar, and we can avoid water. That's exactly how chemists approach the problem, and what they've come up with is a whole plethora of possibilities. The one that your book gives you is another chromium reagent. And as this quote shows, being able to selectively oxidize an alcohol to an aldehyde is really important. There are many possibilities. The chromium reagent the book goes into, PCC, is one of the ones most often used, but I'm going to introduce some others that help us do what we need to do as chemists and avoid the use of environmentally ghastly and terribly toxic reagents to come up with a more green and sustainable way of carrying out the reactions we need to carry out. So I will not be covering pyridinium chlorochromate at all because the book covers it quite well. Again, the key point here is that because of the presence of all these carbons and hydrogens, I can dissolve my PCC in a non-aqueous solvent, typically dichloromethane. It's not real soluble in dichloromethane, as you might imagine, because of the fact that it's a salt. But I want to introduce you to some other reagents that you could use that are a lot nicer for you and the environment. So, green chemistry alternatives for oxidizing alcohols include a reagent called oxone, which is essentially potassium peroxymonosulfate. So what I want to show you here is, of course it's an oxidant. It has a peroxide bond. So that means something's going to happen that is going to allow this thing to deliver an oxygen, making it be in turn reduced. A really good green chemistry alternative is bleach. Sodium hypochlorite, that stuff you get at Willie's. There it is. So, the reason I've got this up is to kind of pull oxone and bleach together and show you that you can come up with a way to catalyze the use of oxone that actually makes bleach. Okay, so you can imagine just protonating your bleach would give you this guy. That's the active reagent. That's hypochlorous acid. All right, that's electrophilic chlorine. That is chlorine waiting to be reduced. All right, so here's the mechanism. You don't have to memorize this mechanism, but I want you to look at it carefully, because what I want you to see is that here's my nucleophilic oxygen of my alcohol attacking the electrophilic chlorine, and what's happening here? Well, it's just a substitution. I am kicking out a tremendously good leaving group, right? I'm just kicking out water and putting that tremendously good leaving group that wants to be reduced, hint, hint, onto my alcohol. So here it is. I put the chlorine onto the alcohol. Obviously, I have the key species I need for the oxidation to take place. So my water right here can rip off that hydrogen, send the electrons to the oxygen, and reduced my chlorine right there, went down to Cl minus. So doesn't matter if it's oxone, doesn't matter if it's bleach, PC's evident. All right, the last oxidizing agent that I would just point out is something called Periodinanes, or hypervalent iodine. It's just kind of a funky, wild reagent. Who knew iodine could have that many bonds, right? Well, if you like this, you should take inorganic chemistry, because iodine can do all kinds of crazy things. But again, here's the setup. Your alcohol is basically going to replace that hydroxyl group. So here it is, waiting to be oxidized. And all I need to do is, well, I'll just use a generic base here. Maybe I'll use an amine. All right, and so boom, boom, and reduction of that really highly oxidized iodine gives me my carbonyl. So that's oxidations of alcohols in a nutshell. The other reagents that, oh, and again, just, I think I've hammered this home. You know what the key step is. Reacting the alcohol with something to put a good leaving group that wants to be reduced, and then ripping off that hydrogen. Again, cannot possibly overemphasize that that hydrogen is on the same carbon as the oxygen. That's what's required. Okay, the book goes through some other great oxidizing agents. Potassium permanganate is a good one, and I will do a demo for you on just how good of an oxidizing agent potassium permanganate is. But basically, no pun intended, because yeah, potassium permanganate is typically done under basic conditions, which is important because all of the chromium plus 6 reagents are done under acidic conditions. So if you have a substrate that is acid sensitive, you can't use chromium, but you could use permanganate. Without going into the gory details of the mechanism, let's just point out that just like the chromium reagents, you can see that permanganate is highly polar. Obviously, it's a salt, potassium permanganate, and so it's going to require water to dissolve, so I'm not going to be able to selectively oxidize with this reagent. This is the intermediate. You know the rest. Now, with all this oxidation under our belt now, particularly ending up with, permanganate, an important question for you. Did you know about the Ganese tribe? Did you know that the males of the Ganese tribe have a special name? Yeah, of course. They're the manganese. That one is really a stretch. All right. That's all you could ever want to know about oxidation, at least for now. See you in class.